Hello guys. Today we're going to take a look at the basic, like it is our first physics lecture, so I'm kind of yeah. So, uh, in our world, in the Newtonian mechanics, we assume that the world we live in is a 3D world. So the 1D world is defined by a straight line, just a straight line. So how do we define a straight line? It's a hard question. So a straight line is defined by like if you have a direction, if like if you have a direction like north, if you just go to the north, just always pointing to north is a straight line. Uh, it's kind of hard to like, yeah, it's kind of hard to like, yeah, define, or you can define a straight line, like the straight path of the light. The path of the light is a straight line. Yeah, you also can define this, but this is not a very good definition. So the better definition just to define it by just a line moving in a certain direction. And for 2D, it is a plane. The plane is just the combination of lines. Like you can describe it like by just using lines in two different directions. So for this point, you can define it by this, in this direction, expand it here, and for lines in this direction, you can expand it to here. A plane, is just a space that can be described by lines in different direction. And for 3D, you can define it by like a plane and a line that is not in the plane. Just other point can be described as this. Like if you take a over here, it's over here, and plus a line is over here. And for this kind of, you expand the plane and you draw a line over here. It can describe all this point. So basically, you can describe all the points in 3D. Oh my god. And now, how do we define length and time? It's a difficult question, you know. It's kind of difficult. So the basic definition is that we find a stick and define its length to be like 1 or 1 meter. We just find a stick and define it. And for like other object like a car, we can find the length, but just like putting this all together and find this length, like you can find it as 3 meters. And I think the best definition might be using the Planck length. So it is the shortest length that in the physical world we live in. So like you can separate lengths into like smaller lengths than this. It is the smallest length like exists in the world, and there's no point of talking about the smaller length than this. So we can define it as a unit of 1. And for like bigger object, we just add up the Planck length. Like in this case, the Planck length is just 10 times the length we defined. But in this world, we just define the length as to be like a length of a stick. And we also can define time by the interval of Planck time, which is the shortest time. like in the quantum mechanics world, uh, like everything is discrete. Like length is discrete. It has the smallest, and it is not continuous, and can be not separated to smaller length, and same as time. So 1 second is can be like put into like smaller parts, like it's just 1/TP. Like how many parts of this? Uh, but uh, but we define time like using like this atom. I kind of forgot what it's called. It's like the electrons between the like different energy levels. It can jump from here to here, and here to here, here to here. Just jumping between two different energy levels. And we define 1 second to be the period or time it like move from layers to layers. So one period is here to here. Here's one period, and the second period is this. So the number of the period it jump like between can be defined as 1 second. And the third like assumption we make is that length and time doesn't change when moving up when like in different frame of reference. What I mean by is that if you stand here and measure a car, the length of a car, it is 1 meter. So if you like you're moving with your toy car in a truck, you also measure this to be like 1 meter. So the measurement doesn't change. So also in the Newtonian world, we like if you measure the car of the restless car, it's 1 meter, and when it's moving, and you measure it, it is also 1 meter. But it is a different case in the like relativity, and we might talk about it in this channel. And it is the same as time. Like in a car, like if you're here and drop an apple from height of 1 m, like it takes the same time as like you drop it from the ground. Like when we're standing here with zero velocity relative to the ground. So it also takes like a few seconds to drop. So the time measured over here is equal to time measured over here. And the fourth assumption we have is that physics laws don't change in different reference frame. So what I mean by is that like if you have like mass of an object over here and you push it with force of m, you still have a acceleration of a. If it is a like car is moving in constant velocity, and if you are standing here and push it, and you have zero velocity relative to the ground, and you apply with force of m, it also like accelerate at rate of a. And it is the same case for law of gravity. Like if you're moving here, then it will just also exert a force of g mm divided by r. And in this, it's also like this. And the constant doesn't change when you're in different frame of reference. And now we're going to talk about coordinate system. So the coordinate system just describing a point in the 3D world we're living. Like here's the ground, and here's like a house over here. If we want to describe the position of the light, we can use a coordinate system to describe this point. And the way we do this is using projectile or projection to the x, y, z. So first, you need to measure the height from the xy plane, so which is called z. So the height is z, and we also need to describe it where it is at in the plane. So if we separate the term into x and y, it can be described as x, y, and z. For all points in the 3D world, we can use this Cartesian coordinate to describe all points. Okay, moving on. And now we're going to talk about vectors. So, you can see, if an object or an apple is over here, and if it moves when t0 changes to t plus changing t0, 1 second to 2 seconds, kind of like this. Its position might change to here. So the position over here is rt, and this one is r2t. So now we need to go over the definition of the vector. So the vector both have direction and magnitude. The magnitude is just basically the length for r. Magnitude is the length of the of this r vector, and the direction is just basically you're pointing to the north, south, east, west, and you're pointing upward, downward. It's kind of like this. And now for vector, we can see that r2t minus r1t is equal to this vector. So yeah, I need to go over this real quick. If you have a stop over here, in a 1D world, if you have a length of 1 and you move it to a length of 3, and this is a point of 0, and we want to find out what is the length of this. So you basically subtract this stuff. So here is a similar case. It's just a projection. So if we take a look at how much, how high the z changes, for the case of r1, you can describe as x1, y1, and z1. R2 can be described as x2, y2, z2. We first want to find out how high it changes. It's just basically z is equal to z2 minus z1. And now we want to find out how many x changes. So it's basically x2 minus x1. And for y is just basically y2 minus y1. So this vector can be described as z2, just whatever, just delta x, delta y, and delta z. And if you for this kind of case, we're going to the 1D world first. So this one is x1, and this one is x2. So this part is basically x2 minus x1. So the same case is over here. So if this part plus this part, it is going to be x2, right? So the similar case over here. So if you have r1 plus this vector changing r, it is going to be r2. Yeah, basically, we can see that displacement is basically a vector that has both like magnitude and the direction. Like can vary from here to here, here, whatever. It has direction. And now we're going to see why velocity is a vector. Like, I don't know why they don't teach you at school. I don't know why. They should. Like, in the case of this, if the time change is really small, then this just like very, very small. We can see that the definition of velocity is equal to the change as limit t approaching 0, change in r divided by change in t. So it's basically this factor. You can see that this is basically dt minus rt divided by t. And from here, we can see this has direction. And this is the direction of the vector. And here, it is just a constant. And it does not have any like direction or stuff. It's just a scalar. Or you can treat it as a number if you want. Or 1, 2, 3. So basically now, if we can, and we see that changing displacement has direction. So if you divide by change in t, it also has direction. And this stuff also has magnitude if you take the the absolute value. Because this has direction, we now can see that acceleration is defined by this. This also has direction. Because velocity has direction. Okay, now we're going to move on to polar coordinate. So for this kind of coordinate, we described the points. Like this is 2D. At the length of the the stick, and the angle between the x-axis and this stuff. And you can see we can describe all points in this. We can describe all points in this plane because, you just can this here, 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 here. Yeah, it's basically can describe all the points in this plane. And I need to add something is that we can also separate this to, wait, yeah, I'm missing something over here. So for the case of r, we can write it out x1, x, y1, y, and z1, z. So basically, it is the direction of x and direction of y and direction of z. This basically has magnitude of 1. It's just a unit vector. What I mean by unit vector is that if you have a number over here, 1, and you time it by the direction, or 2, you basically have a ER. You basically have the length. The vector has length of 2 and the direction of ER. Or in the case of if you have a number of m and time it by the unit vector, it has a magnitude of m and the direction of ER. And we can see that we can treat this as a vector over here. And this is a vector over here. And upward, we can basically describe this point as adding the vector. And so now, okay, move on. we can separate the velocity to the term of x2 minus x1, x direction, y2 minus y1, y direction, and z2 minus z1, z direction divided by the time. So this basically can separate to vx, x direction, plus vy, y direction, and vz, z direction. And for the case of polar coordinate, we describe a vector using like unit vector of e and er. So basically er is a same direction as this, and e theta is a direction that is perpendicular to er, which is a perpendicular to this stick. And if we want to find the velocity, like using the polar coordinate, we just, let me draw the graph over here. It changes from here to here in a very short time dt. And this one is in the direction of this one is basically like r d theta, and we call it theta. And this part is basically dr. Dr is just changing length, okay? So basically, like dr can be described as like, or we'll just put a magnitude over here. So r direction and plus r d theta times the er direction, e theta direction. Wait, is that correct? Okay, wait a second. Wait, that is not fine. That is not fine. Wait a second. So because r can be described as r is equal to r er plus yeah, basically this. And if we take the derivative by the definition of velocity, you can see this is basically dr dt er and plus r dr dt. Basically this. And from this point to here, we can see that we first observe the changing er, which is just basically flipping d theta, and it is in the direction of v theta. If we take a look, like a small change, like we can draw a triangle over here, and if we like this stuff is really small, and this angle is sharp, it's just going to be 90 degrees. You can see is if time is approaching 0, it's just 90 degrees. So we can say that changing er is in the direction of changing of the e theta. So this term is just going to be vr plus v theta, and this is der is going to be e theta d theta dt. So this term is going to be r d theta dt, and in the theta direction. This one is equal to dr dt in the er direction. Okay, now we're going to talk about the elliptical coordinate. So this part is optional, and If you want to stick with me, you can watch it. If you don't want to watch it, you can like quit this video. So for this kind of coordinate, we also can describe x and y and other point using this, because we have like 2 degrees of freedom. So if you change this and this, we can describe other point, because they're independent. They're independent, so we can describe all the points using this. And now we're going to see this C and this one C. So basically R1 and R2. And first we're going to see that. Wait a second. R1, which is equal to x plus c squared plus y squared, which is equal to, okay, wait a second. Okay. So CH cosine square plus C SH sine square. And we can like just put C over here. We have the term of CH square cosine, and this one is just 2 CH cosine and plus 1. And this term CH SH plus sine, and this from a property we know, and we can see. Wait a second, let me see. What is it? 2 for this part, for this term we have CH square minus 1 sine, because we know the property of CH minus sinh is equal to 1. So now we have that this term is just going to be equal to this term times this term, and plus this term is just going to be equal to CH. And this term times this term minus this is just cosine squared plus 2 CH cosine. And now factor it out, and we can see this term is just going to be C. Cosine and sinh, and this one's R1. And by the same way we can find like R2 is equal to C times a negative cosine plus CH. And now for R1 plus R2, this is going to be C 2C times CH. And if this psi is going to be equal to a constant, it is basically describing like this. It just basically an ellipse. And for the case of R1 minus R2, it is going to be RC. This. Really? Oh, wait a second. Cosine. So if eta is going to be a constant, it is just basically describing this. And we know that, or you guys don't know this, or if this and this has the same like foci. I forgot what it's called. Then this is perpendicular. Like you can search out the proof if you want, and I offer an alternative proof is that you basically find x is a term of like this and eta, and the y is a term of this and eta. And for and this blah 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 blah. And if you times the two, you can see they're basically equal to 0. Okay, we're done with this lesson.